So Michelson did this experiment in actually 1881, and he had a null result. He did not find the existence of an ether. That doesn't mean that ether doesn't exist. What it meant was he was not able to measure it to the precision that he wanted to measure it. So he redid the experiment and published the results again in 1887 with Morley. So in 1887, to within the parameters of their experiment, they were not able to determine the existence of an ether. But let's see how that works. And it also doesn't mean there's no ether. The sensitivity of the experiment wasn't terribly sensitive, and it took a lot more information to come around before anybody could say, absolutely, there is no ether, there is no preferred reference frame for light. Remember, that's what ether means, really. It's the medium in which light waves are preferred to or wave in, but it means that there is no preferred, that it would be the preferred reference frame, and if it doesn't exist, there is no preferred reference frame. So let's just look at the Michelson Morley experiment and see why interferometry is actually such a sensitive measure of distance. Okay, this is the basic Michelson Morley setup. Now, I'll explain what's going on here. This is a top view, and we would have this like on a table or in a box. Actually, maybe we'd include the light source in that table or box. And for the Michelson Morley apparatus, this apparatus was about, I believe, about a meter long by a meter wide. It was approximately a meter by a meter, or maybe it was a couple meters by a couple meters, but it was, tabletop sized. And so what you do in order to create an interferometer, interference pattern, is you have a light source. That light source comes in and first hits what's called a beam splitter. All a beam splitter is a mirror that doesn't work perfectly. And it's very easy to create a mirror. All you need to do is take a piece of glass. Well, actually, glass itself is a beam splitter, because glass, as you know, if you look at any window glass, it both reflects light and transmits light. And that's what a beam splitter is. But what you can do is you can actually take silver and you can evaporate a silver layer on top of a piece of glass, and the more silver you put, the better a mirror it makes. So you can vary the amount of reflection versus transmission. In any case, with the beam splitter, when the light, and in this case I'm drawing a red light like it's a red laser. Keep in mind that Michelson Morley didn't have lasers, and so they would have had to use some other collimated light source, but today we would use lasers. And so we have this light that reaches the beam splitter. Oops, and I drew this a little bit off, but we'll see. And so what happens is it reflects off the beam splitter like a mirror, but it also transmits through the beam splitter. So there are two paths. We're going to call the transmission, the straight path, the path 1, and we're going to call the reflected path, path 2. Two different paths, so it splits the beam into two. Now, what happens along the two paths? Path 2, let me follow that. Let me change the color. I'll change it to purple, just so you can follow path 2. Path 2, it goes up to the mirror, and this is where I didn't put the mirror in the right place, but it goes up to the mirror, bounces off the mirror, and comes back. At the beam splitter, it'll again split into two. It'll bounce back to where it came, but it'll also transmit through. All we care about is the transmission through. Now let's look at path 1. Let's keep path 1 red. Let's think of that as our primary path. It goes to the mirror, bounces off, comes back to the beam splitter. Some of it transmits through, but some of it bounces down towards the screen. So it's these two that go down towards the screen that we care about. Oops, hold on a second. It's these two beams that we care about. Okay, so when these two beams, and they're both, whatever, the same color light, I didn't really mean to change the light, get to the screen, they reach the screen, and they interfere on the screen. And what you get on the screen is you get an interference pattern, and you'll get a series of dots like we showed for the light interference pattern before. Oops, let me do a color we can see. Get a series of dots along the screen. I guess if it's red light, they're going to be red dots, not green dots. So, one more time. I'm just going to trace it with a different color. We've got light that comes from the light source. It goes straight through, bounces off the mirror, and comes down to the screen. Let me try that one more time. Light coming from the light source, goes straight through, bounces off the mirror, bounces off the beam splitter, comes to the screen. We have a different color of light. Not a different color of light, it's the same light. We have the light, which also bounces off the beam splitter, goes to the mirror, bounces back, and comes straight through. Those two beams interfere at the screen, and we get an interference pattern. Okay, so far it's not an interferometer, it's just an interference pattern. But let's see what makes it an interferometer, what makes it a length measuring device. So in an interferometer, we're looking for something, the properties of something perhaps, that will slow down the beam or shift the beam. So for example, maybe the mirror, one of the mirrors, is attached to something that we're trying to measure a very small amount of motion for. Right, so let's attach the mirror. Let's just take one of these mirrors or both of the mirrors and attach it to something. Right, so the mirror is attached to a big ball, and we want to measure the motion of that ball. Let's say the other mirror is fixed in place, and let's put it in the right place because I've shifted it over. Okay, and now if the object, which the mirror 1, I'm going to call them M1 and M2 for mirror 1 and mirror 2, if the object for which mirror 1 is attached moves, right, the path for the path 1 is going to change, and path 2 will stay the same. And so the change in path will shift the interference pattern on the screen. The change in path, so if I shift M1, the mirror M1, back or forth, it's going to change the path length, path 1, and that is going to change the interference pattern on the screen. Let's see how that is sensitive to distance. But before I do that, let's just talk about the other way we can change the path. Instead of moving mirror 1 or mirror 2, what we can do is we can put something in the way of the light. So for example, again, let's say that we have the original setup, and now I want to measure the properties of a gas. Maybe I want to measure how fast light moves through the gas. In other words, the index of refraction. What I can do is I can put a container of gas here, right? Something which the light can go through in the way of the beam. And so what that gas will do is it will slow down the beam. And when the gas slows down the beam, that is the same. If slowing down the beam, it still shifts the light going along path 1 relative to path 2 because it slows down a peak. And so what that does is it shifts the interference pattern. And when I say shifts the interference pattern, I mean it shifts it left or right, and it'll shift the interference pattern. So what I need to show you is how sensitive the interference pattern is to changes in path 1. By either, or path 2, we could do this to path 2 also, but by either moving the mirror or putting something in the way to slow down the beam. That's what an interferometer is you see shifts in the interference pattern due to changing one of the paths of the light, the length or the time of transit of one of the paths of the light. So that's what we want to do next. Now we're going to do the math to show how this interferometer works and how sensitive it is. And then we'll talk about how Michelson and Morley use this to measure the ether, or to look for the ether.